So just as a reminder, what we did last time. We discussed representations of compact p-adic groups. By analogy with representations of compact real groups, compact Lie groups, we observed that in contrast to the real situation where they exist in abundance, there are not many compact p-adic groups. They're mostly division algebras. I chose to focus exclusively on the quaternionic division algebra case. The prime degree division algebra case is pretty similar. There are a couple additional complications I'll get to later today. The composite degree case evidences a lot more complications. But what we saw last time really gave us the flavor, which I'll just remind you of how it works. The theory of the highest weight So on the compact Lie group side, the theory of the highest weight, or parametrization by highest weight, was replaced on the quaternionic side by a parametrization by torus character pairs. If you're familiar with representation theory over other fields, this is going to look very, very familiar to you. This is the same way it works over the reals when you try to parameterize discrete series representations. This is, loosely speaking, the same way it works for finite groups of Lie type when you're trying to parameterize Deligne-Lustig representations. This is the kind of parameterization you'd expect, that at least some large class of representations is described by torus character pairs. I won't address that to Nat, who likes representations of unipotent groups, but for those of us who like reductive groups, this is the kind of parameterization that you'd expect. The Borel-Weber theory, or Borel-Weber theorem, which allows you to realize representations in spaces of global sections on a certain line bundle. To put it differently, in certain induced function spaces, is replaced by realization in a compactly induced function space, or I'll say induced from compact function space. Which I wrote down last time. And the Weil character formula is replaced, and I didn't make this clear last time, so I want to say this in a loud voice. The Weil character formula is replaced by a similar character formula Similar means it involves 1 over the square root of the discriminant, a linear combination of Weil conjugates of your parameterizing character, and that formula is valid on the parameterizing torus. This is exactly what you'd expect, exactly what you get in the Weil character formulation, except there's a wrinkle in the p-adic case that this similar character formula is true only far from the identity. As you may or may not remember, we had this final condition that said if you're in E cross but not in F cross times 1 plus the prime ideal to the n, then here's your character formula. And we need a completely different looking character formula once you're within depth n of the identity. So what I want to do today is describe how this whole picture changes in the general case. What happens in the general p-adic case? And just as a reminder of our notation, F here is going to be a p-adic field. We don't assume that it's characteristic 0. It doesn't much matter. Makes you happy. You may assume that it's 0, but we don't need to assume that it's 0. But we will assume that P, bless you, is very large. In particular, P for this talk is never going to be 2. And frequently, we have to throw away a couple of other primes as well. For example, if we're working with GLn, we have to throw away primes dividing n. G, regular G, is going to be the group of f rational points of bold G.
Is the bad thing primes dividing the order percent?
It's these things that I forget whether we need to throw away bad primes or torsion primes. I can't. If you throw away bad primes and torsion primes, you're fine. I think it's the torsion primes that cause the trouble. These are the ones that say your centralizers of semi-simple elements can behave in some unpleasant way. So regular G is going to be the group of f points of bold G, which is a connected reductive group, and we want to see what can we say about the representations of G. Well, I want to remind you from Alan's talk that we have a sort of reduction map that says if I give you a pair G comma pi, if I give you a representation pi of G, and pi here is going to be a smooth, irreducible, therefore admissible representation. I'm not going to write down a lot of these words because I'm going to, well, why not? This is smooth, irreducible. Then I can manufacture from this guy a pair L comma sigma, where L is a Levy subgroup and sigma is a supercuspidal representation. Such that pi appears as a sub-object in some induction from a parabolic P containing L of sigma. I put reduction in quotes. We often will go the other way. We'll often start with the Levy-Cuspidal pair and induce it up and look at the subquotients. But we could view this, if we wanted to, as a map from its representation to this pair L sigma, which up to a suitable notion of equivalence is what Alan was calling the cuspidal support. Well, in the extreme case, by the way, I'm going to use this to define supercuspidal, which is going to sound a bit circular since supercuspidal is involved in this notation here, but you could phrase it in a way that avoids all the circularity. I just want to give the flavor of what's going on. In the extreme case, the best reduction you could possibly get is the case where L equals A is a split torus, in which case all representations of a split torus are cuspidal or supercuspidal because it's defined in terms of the behavior mod center, and it's all center. The irreducible representations are just characters. So in the extreme case, we're inducing off a character of a split torus extended trivially across a Borel subgroup. And in this case, apparently everyone but me says that pi is in the principal series. I say it's a subquotient of something induced alpha Borel. But Monica correctly points out this doesn't roll off the tongue. So for now in this talk, that means that pi is in the principal series. So that's the extreme case. The most reduction you can get, or I should say maybe extreme case is, this is the most reduction you can get. On the other hand, the least reduction you can get is none at all when L equals G, in which case sigma equals pi. And the representations, so this is case 1, and this is case 2, and the representations for which you have no reduction at all, the sort of primitive representations. I'm sure somebody out there has a technical meaning for primitive. I just mean reduced as much as possible. The primitive representations for this reduction are called supercuspidal. So the idea when you're dealing with representations of any group, when you want to understand representations of any group, is that this never happens. You never understand the representations of a group. So the next best thing you can hope for is you can replace an understanding of the representations of a big group G by the representations of a smaller group L. At bottom, you're going to be replacing your big non-abelian group by a torus, and then we want to reduce everything to the study of linear characters, of one-dimensional homomorphisms to C cross, which we also don't understand. Anybody challenges you to write down a list of these, have fun doing that, but at least we pretend we do. These are very tractable ingredients. So this is our idea. Everything proceeds on the basis of reduction to smaller groups. So from the point of view of the Bernstein decomposition, this is as far as you can go. If you've got a supercuspidal, there's no more reduction to be done. This is, if you're doing hard analysis, if you're doing harmonic analysis, this is where the hard work comes in. First prove some kind of reduction to the cuspidal case, and then you prove whatever you need to prove in the cuspidal case. But I would like to reduce further. And it turns out there is a further reduction due to many, many, many people, and I'm not going to try to list all the names because that would inevitably insult somebody by leaving them out. I'll just mention a couple of the highlights. There's Corwin Howe Moy, who I wrote out last time, so I don't have to do it again, from the late 70s. There's Larry Morris from the early 90s. Jeff Adler from 98, and then kind of the culmination of this line of thinking, not the only approach, but the culmination of this line of thinking came with JKU in 2001 that says you can perform a further reduction when pi is supercuspidal. And p is large, yes. And usually it goes the other way. Usually you start with the reduced object and build up pi, and in that you can do that regardless of p. You just won't get everything. Pardon? Kemp? Oh, Kim. Yes, for exhaustion. Well, yeah. Which is probably 08. So we have a further reduction. And for that matter, the way I'm stating it, we should put Jeff and Fiona, which I think was also in 08. See, it's no good trying to list all the names of people who contribute to this. Then we have a further reduction from the pair G pi to a pair G prime pi prime, where the reduction is defined by put prime on everything. And here pi prime is a supercuspidal representation, again, of smaller depth. And G prime, well, it can't be a levy anymore because by definition, supercuspidals are the ones where you cannot reduce the levy subgroup. But what we get instead is what's called a cuspidal twisted levy. Twisted just means it becomes a levy after base change. So you can think of something like GL2 over a quaternionic, over a quadratic extension sitting inside GL4 over the ground field. The cuspidal part just means that the center of the big group mod the center of the small group is compact. So we get a similar looking ingredient. We get a supercuspidal representation of a subgroup, but now our subgroups are no longer honest levies. They're levies after base change. And in fact, they're as minimally rational as possible. Their centers haven't increased at all in the split, the split part of their center hasn't increased at all. Exactly, yeah. All right, I suppose one should say there's no parabolic containing it that's defined. I mean, you need to really be as irrational as possible to have this compactness condition. But yeah, that's what this means. That it is a levy component of some parabolic subgroup. It's an F subgroup, but the parabolic is not an F subgroup. Okay. And so the extreme case is here. Well, you'll obviously no longer be able to get down to a split torus because except in the anisotropic case, a split torus is not compact mod center. except in the trivial group case. You know, in very few cases is a maximally split torus going to be compact mod center. But you can get down to the case. Yeah, right. You can get down to the case of an elliptic torus, in which case, again, pi prime will be just a homomorphism from T to C cross. And there's no particularly good names for these guys. You might call them the representation pi very toral, but don't bother remembering that terminology because everybody's going to make up their own words. So that's the extreme case when you can reduce all the way down to a torus. The opposite extreme is when you, again, cannot reduce at all. I know you can't see that. I'm sorry. I'll move it down in a minute. The other case is when you cannot reduce at all, in which case your pi prime is just your pi. And in this case, pi prime is a depth 0. Supercuspidal. I'm not going to get into the whole machinery of depths, but what depth 0 means is that it comes from representation of a finite group of Lie type by inflation and then induction. And then that finite group of Lie type, that representation of the finite group of Lie type, that might be a Deligne-Lustig representation, in which case finally at the bottom you've got a torus character pair, but it also might not be a Deligne-Lustig representation. So what I want to point out here, the purpose of going into all this discussion without giving any details is that we cannot always reduce to torus character pairs. I don't know if he remembers, but I remember very fondly a conversation with Jeff Adams in Kalamazoo where we were having dinner after an AMS special session. He said, wait a minute, are you telling me that not all representations of p-adic groups come from torus character? Really? They don't? Not in any way? Not all? Okay. So no, it's true. You cannot reduce a representation of an arbitrary p-adic group down to a torus character pair, even a supercuspidal representation. So this is what replaces the theory of the highest weight. Instead of parameterizing by torus character pairs, we parameterize by pairs of a twisted Levy subgroup and a cuspidal representation of smaller depth. And eventually we have to stop once we hit a depth 0 representation. What's the replacement of Borel-Weber-Bott? I'm going to make a baffling statement for simplicity. The following statement is for simplicity for now. What does that mean? That means for now I don't need it. For now I could drop that assumption and everything I say with suitable modifications would still be true. But eventually I'm going to honestly impose this hypothesis, and it's mathematically required rather than just required for exposition. So for simplicity, for now, let's suppose that G prime mod the center, not just the center of G prime mod the center. Let's suppose that that's compact. That makes life a little bit easier.
Center of G or
G. Although it's equivalent because the center of G prime is compact mod the center of G. All right, well then we essentially proceed as before. Essentially via extension and induction, we have this representation pi prime. It lives on G prime. We extend it so that it's defined on some compact open subgroup, and then we induce off that compact open subgroup, and that'll be our representation pi. I'm sort of reversing this map now. I'm trying to start with G prime pi prime and construct G pi. But, well, it wouldn't be very interesting if there weren't anything new, but there are two new ingredients. I put new in quotes because that's a bit of a lie. They're not new in the sense that both of them are already present in the work of Corwin, Howe, and Moy. First one in the work of Corwin, Howe, Moy on general linear groups. Second one actually occurs already in the setting of division algebras. They're just new to us because I imposed so many simplifying assumptions the other day. What are these new ingredients? One is, well, we have to replace the canonical filtration of your division algebra, multiplicative group of your division algebra, by multiplicative group of its ring of integers, 1 plus prime ideal in the ring of integers, and so on. We have to replace it by something else because a general p-adic group just doesn't carry such a filtration. And the solution here is to use Moy-Prasad subgroups. These were defined in 94 and 96. We use Moy-Prasad subgroups, which are indexed by points of B of G. Now, I'm sorry, I already referenced Alan's talk, but I'm afraid I have to disagree with him on notation. Today, B of G means the Bruhat-Titz building, not the Bernstein spectrum. If you're familiar with the building, you know what I mean. If you're not, here are two examples. The same two examples you'll probably see in any talk that mentions the Bruhat-Titz building and doesn't go into detail because otherwise it gets pretty complicated. If G is GL2Q3, then the Bruhat-Titz building is a 4 regular tree. I specifically chose GL2 rather than SL2 so that you know that I'm talking about the reduced building when I say that the building is a tree. I'm only going to draw a little bit of it. So it looks like this, extending out forever. And it's got 2 points that I want to single out. There's a vertex called x1, and then there's the midpoint of an edge joining x1 to some other vertex that I'm going to call x2. And the Moy-Prasad Moy-Prasad subgroups associated to these guys recover the standard filtration of the maximal compact and the Iwahori filtration in the following sense. So G x1 0 is GL2 over the ring of integers, which I suppose I should call Z3 since I named the field Q3. And G x1R, these filtrations are indexed by a pair of a point in the building and a real number, a positive real number or non-negative real number. This looks like 1 plus the rth power of the prime ideal rounded up times 2 by 2 matrices over the integers for R positive. So this is the standard filtration of the maximal compact, GL2R. On the other hand, if I look at the filtration associated to x2, associated to this midpoint of an edge, it's going to look like the Iwahori subgroup at depth 0. If I try to go a little bit further down, I might as well go to depth 1/2, in which case I get the pro-unipotent radical of the Iwahori. and then I continue in roughly this vein. The next step down comes at depth 1, where I essentially multiply everything here by p. And so on. So these are the filtrations of GL2. You get more elaborate block filtrations inside GLN, depending on the factorization of n. But those are some familiar filtrations. If G is a division algebra, case we were interested in before, then B of G is a singleton. So there's a canonical filtration, and you'll never guess the canonical filtration is just the canonical filtration. To keep things definite, I'm going to say it's still a quaternionic division algebra. Then the depth 0 term in the filtration is the multiplicative group of the ring of integers. And the depth R term in the filtration looks like 1 plus the prime ideal to the 2R, rounded up for R positive. So the canonical filtration on a division algebra, the only filtration that it carries is actually a Moy-Prasad filtration. In circumstances where you don't have a canonical filtration, you nonetheless have this family of filtrations. And we want to somehow pick out an appropriate filtration for G. How are we going to do that? Well, in general, if G prime mod its center, and as Terence pointed out, I might as well say G prime mod the center of G, or G prime mod the center of G prime. It doesn't make any difference. If this guy is compact, then it's always going to happen that its reduced Brouhat-Titz building is a singleton. And since the Brouhat-Titz building of a twisted levy, I forgot to say this, but these twisted levies don't admit arbitrary base change. They have to behave well after tame base change. So I want it to become a levy after tame extension. Then it's true that the building of G prime sits inside the building of G. So we've picked out, by virtue of choosing this compact mod center subgroup, we picked out a canonical point in the building of G, which means we've picked out a canonical filtration. So that, I talked about it so long you might have forgotten, but I was trying to describe the two new ingredients that occur when we try to generalize from the quaternionic division algebra setting to the arbitrary setting. The first new ingredient was a replacement for the canonical filtration, and we've got now a new canonical filtration. The second ingredient is we can't always extend as far as necessary. I'm going to explain this by slinging around some notation that if you haven't seen the Brouhat-Titz notation before, is going to be a little, or the Moy-Prasad notation before, it's going to be a little scary. But just for the experts, here's what's going on. If your representation pi, which is the representation of a compact group, so it has a kernel, compact p-adic group, so it has a kernel. If your representation is trivial on GXR plus, but not trivial on G prime XR, then we can extend more or less as before. I'll just say trivially across the perp space. to G prime times Gx R over 2 plus. We can extend it just a little more than half the depth. But what we actually need, it turns out, for all the intertwining calculations to work and for the induced representation to be irreducible, we need to live on G prime times Gx at precisely half the depth, not just over half the depth. Now, the way the Moy-Prasad filtration works, as you may notice from looking at these formulas, there's some rounding up involved. These filtrations for different numbers r can look the same. If I increase r a little bit, I might change the subgroup, I might shrink it, or I might not. So for all I know, these two subgroups might be the same. In fact, they always are the same for ramified representations of quaternionic division algebras, which is exactly why I set things up that way. But they will not always be the same. It turns out that somewhat, this is not really magical, but it's very surprising to me. The surprising fact is that buried in this local fields picture, well, there's no surprise that there's finite groups lurking somewhere around, but here is a place you wouldn't necessarily expect them. G prime G x r over 2 mod G prime G x r over 2 plus, the quotient that measures how far we want to extend compared to how far we can extend. This is naturally a symplectic space. A finite symplectic space. I'm not going to tell you where the symplectic structure comes from, except that it comes from the datum pi prime. And we can use a finite Weil representation to get all the way to G prime G x r over 2. Then we induce from that subgroup. There we can induce irreducibly, and that's how we get our representation pi prime. Sorry, pi. Yes?
What does P have to be large?
At this point, P has to be even, odd. Because if P is even, we don't know how to handle the Weil representation. But other than that, any P is fine here.
What's the extent across the first space you don't need P to be large?
No, because here I'm using that G prime is a levy, so there's a natural perpendicular, which is the sum of all the root spaces that are outside G prime. G prime is also tame, and requiring G prime to be tame puts certain conditions on P. I mean, for there to exist a tame torus at all. I guess that's not true. I guess there'll always exist. Anyway. The only overt condition right now is that P is not 2. OK, so far I've told you how to replace the theory of the highest weight, and I've told you how to replace the Borel-Weil-Bott construction. This may not look much like Borel-Weil-Bott at this point, but if you view Borel-Weil-Bott as a statement about induced representations, that's exactly what's happening here. So what about wrong color? What about the Weil character formula? Well, as you may have noticed from my clever prestidigitation, if you are blind to green, then you'll read what about the character, and that's a valid question too, because the representations pi we consider are, I'm just going to leave off any qualifier, they are almost always infinite dimensional. So trace pi of g probably doesn't make sense anymore. You've got an infinite dimensional operator. It may have a trace, it may not, but there's no guarantee that it has a trace. And in fact, if we're talking about unitary representations, which is the case of most interest to me, it is guaranteed not to have a trace. So this guy might not make sense. And in the case of most interest, it definitely won't make sense. So the solution, which is due to Harishchandra in the 70s, I'm not going to go into any detail about it. I'm going to dramatically shortchange this very deep theorem. Is to mimic the real case and say, okay, I can't trace individual operators in the representation, but I can trace certain weighted sums. To replace by weighted sums as follows. We look at the integral of pi of g with respect to Haar measure, and I don't have to say whether I mean left or right Haar measure because under our restrictions, g is unimodular. Integrate pi against such a function. I've got an operator on the representation space, and it turns out for a rich class of test functions, this will always be trace class. And the claim is, the theorem due to Harishchandra, is that I can find that trace by integrating my test function against a suitable function theta sub pi, which is called the character. There's all kinds of nice things you can say about its character. You can talk about its integrability, except I haven't assumed characteristic 0, so I don't want to. You can talk about its singularities. You can talk about all kinds of things, but for now I'm just going to say it exists. Okay, so I started off asking the question, how do you get a character formula? And I briefly diverted to talk about, does the character even make sense? Now we know it does. How do we compute it? Well, Jeff and I computed the formula and the funny thing is, I don't want to say this on Jeff's behalf, but I'll say it on my behalf. The funny thing is, you can take this as a testament to the genius of Corwin and Howe or to the lack of genius of me. No really fundamentally new ideas were needed. You just pushed really, really hard on the Corwin-Howe argument. And it's here that we really need the assumption that G prime mod the center is compact. Before that was just for convenience. Now we honestly need that assumption. We do not have character formulae without this assumption. And so the outline is the same as before. Which, just as a reminder, looks like this. You've got a representation induced off some compact open subgroup, but it's far from maximal. So you induce up to another compact open subgroup, which is still far from, well, which is closer to maximal. So induce partway. And again, in case you're familiar with the notation, the subgroup to which we induce is G prime times GX0 plus, which is, if you're familiar with this stuff, exactly a perfect analogy of E cross times 1 plus the prime ideal, which is where we induced to before. Then we show that the partially induced character vanishes off H conjugacy classes intersecting a much smaller group than you have right to expect, which for us is G prime times GXR. This is much smaller than the inducing subgroup, so much smaller than naively you would expect the support to be. This guy is the analog of our E cross times 1 plus PD to the n in the division algebra case. And then in the case where you are in this subgroup, where the character isn't known to vanish, you group terms until you can control what's left. Now, once again, there's two new ingredients here. The idea of the philosophy, the broad outline is the same, but there are two new ingredients. One of them is due to this same paper of Harishchandra from the 70s, these Van Dyck notes, which is we don't have a Frobenius formula anymore. We're inducing off a compact open subgroup up to a non-compact group, so it's infinite dimensional, so you can't just naively write down Frobenius formula. There's no reason to believe that it converges. But for supercuspidal representations, Harishchandra proved a similar integral formula. Later extended by Rader and Silberger to handle the discrete series case. And to the best of my knowledge, this is essentially the only tool we've got for computing characters. There's also Van Dyck's formula for a full parabolically induced representation. That's about all there is for computing p-adic characters. So that's one ingredient. And the other ingredient is the following not lemma, which says that if gamma is in G prime times GXR, then gamma is H conjugate, minus the center times GXR. If that's true, then gamma is H conjugate to an element of G prime. What do I mean by not lemma? I mean it's false. Well, who cares? Well, remember last time we had this crucial idea that if gamma was in E cross times 1 plus PD to the n, but it wasn't in F cross times 1 plus PD to the n, in that situation, you could conjugate gamma into E cross. And I warned you that that was the statement that all regular elements were very regular, which is true for a quaternionic division algebra, true for a prime degree division algebra, badly fails for essentially every other group. For example, it's false for a degree 4, dimension 16 division algebra. It doesn't sound like much. It sounds like such a small thing. OK, so you can't conjugate into there, so no problem. But it turned out we need a whole other 80-page paper to address this. So Jeff and I define a decomposition gamma. This is my notation. I alone am to blame for it. Gamma equals gamma sub less than r times gamma sub greater than or equal to r, that essentially measures the failure of this lemma. So in particular, our conditions, if gamma is close to our parametrizing twisted levy, if it's in G prime times GXR, then it may not be conjugable into G prime, but at least gamma sub less than R, which Jeff more mnemonically calls the head, lives in G prime, and gamma sub greater than or equal to R lives in GXR. So we might not be able to conjugate away that depth R piece, but at least we can meaningfully say which piece of gamma actually lives in G prime and which piece of gamma actually lives outside. So in terms of all those ingredients, we have the following theorem. Here, yeah, if you want to say that this exists for all elements gamma, then P has to be large. Otherwise, you can do it again. You can say there are some elements gamma that have such decomposition. That's true. We were quite careful. This 2008 paper has a ridiculously general list of hypotheses. For example, in this paper, our field is no longer p-adic. It is a finitely ramified extension of a discretely valued field, algebraic extension of a discretely valued field with perfect residue field. I think that's what we wound up having to assume. Ridiculously general list of hypotheses that are of no use whatsoever because no one is ever going to use it except in the setting of p-adic fields. But that's true. You never know, which is why how Jeff talked me into it. All right. So in terms of all these data, here's the character formula. Character value at gamma looks like a sum over delta, and I'll say what delta is in a minute, of the following mess of notation. C of delta times fractor G, of delta less than R times theta pi prime of delta less than R times mu hat upper M sub x star of the log of delta greater than or equal to R. And if you're feeling really, really sympathetic, you can vaguely see this as an analog of the Weil character formula, but probably not until I tell you what some of this notation means. Yes?
So in this decomposition,
Yes.
would you say that gamma is conjugate to such a product, or it literally is?
This decomposition behaves well under conjugation, so it doesn't matter. So if gamma were conjugate, then its head would be conjugate into G prime, and its tail would be conjugate into GXR. Yeah, and I was actually about to say that. But yes, you should think of that as an analog of the Jordan decomposition, or if you're comfortable with it, the topological Jordan decomposition. Everything OK? Or some things OK anyway? Where delta essentially runs over G conjugates of gamma that live in G prime times GXR. So a particularly boring consequence of this is that if no G conjugate of gamma lives inside G prime times GXR, then the character is 0. What do I mean by essentially here? I mean that I want to count two terms as the same if the head of delta, the heads of the corresponding deltas are G prime conjugate. No condition at all if G prime is a torus. C of delta is an explicit positive real number involving Weil discriminants. So remember that this is what you expect to see in a Weil-type character formula. You expect to see out front a denominator of 1 over the square root of the Weil of the absolute value of the Weil discriminant of gamma. It's a little more complicated than that here. We have a couple more Weil discriminants floating around. We have the Weil discriminant on G prime for example, floating around. But basically, that's what this positive real number is. It's explicitly described. I should say explicitly computed. Because I want to compare it to this fractor g of delta less than r, because this is an explicitly defined fourth root of unity. I know this is not a linguistics class, but what's the difference between explicit and explicitly defined? Explicit means you give me a delta, I tell you what C delta is. It's no problem. Explicitly defined means you give me a delta and I tell you how to sit down and compute this fourth root of unity, but I have no idea off the top of my head what it is. Yeah, a Gauss sum and the Weil representation. So yes, if you're willing to accept Gauss sums as primitive ingredients, then I can tell you what it is, no problem. Theta sub pi prime is the character of pi prime. Not much to say about that, except I want to point out that we're possibly evaluating that character at a singular element, which you might say, whoa, wait a minute, I didn't say it here, but wait a minute. Characters are a priori defined only. You should always turn off the ringer on your cell phone. Characters are a priori only defined at regular elements. How are you evaluating this character at a possibly singular element? And the answer is this is a character of a compact group, because I said so, and characters of compact groups are everywhere defined. And M is the connected centralizer of the head of delta, which again might be bigger than a torus if the head is singular, and mu hat upper M sub x star is the Fourier transform of a semi-simple orbital integral, semi-simple orbital integral on the Lie algebra of M. So these are all the ingredients.
This is all on characters of 0.
No. This is all true in general.
Log.
Log here means the inverse of our Mach exponential map, which is the analog of that x goes to 1 plus x map from before. The existence of such a map in general was proven in Jeff's thesis, so we just take a suitable map. We have to be a little bit careful about how we choose it. We take a suitable map and we take its inverse. That's all. Pardon? One more time?
Is this far away from the identity or is it?
No, this actually holds everywhere, and the decomposition takes care of having to say far from the identity or close to the identity. For example, if we are close to the identity, all this drops out. And we just get a Fourier transform of an orbital integral. Far away from the identity, all these terms are important. I'm, in fact, going to say a little bit about that. In fact, possibly Sandeep has been reading my notes because he brought up exactly two of the remarks that I wanted to make. One remark that I wanted to make is that this fractor G is defined in terms of a Gauss sum and the finite field Weil representation. So both of those ingredients come into play, and it turns out this ingredient interferes with stability in a sense that I'll talk about later. Another point that Stephen mentioned is that this decomposition of delta into a head and a tail should be thought of as an analog of the Jordan decomposition over a finite field. In fact, if R is a very, very small positive number, then this literally is the topological Jordan decomposition over a p-adic field.
Do these things commute at least up to something small?
Yes, they commute on the nose. Yep. Which is why a theorem like this can be hard to prove, because otherwise you could just say, okay, it's a G prime thing times it, right? But the point is you can write as a commuting product of such elements in a more or less canonical way. So once you see a character formula that involves an analog of a Jordan decomposition, you might stop thinking of the Weil character formula on the compact side, because there's no Jordan decomposition on the compact side. And you might start thinking about a Deligne-Lustig character formula, because a Deligne-Lustig character formula looks like something, character values, evaluated at the semi-simple part, times something, green functions, evaluated at the unipotent part. And indeed, that's exactly what's happening here. Right. So this, I can perturb each of these guys a little bit, but it doesn't change the centralizer, the connected centralizer of the head. So the orbital integral, mu hat upper m sub x star, is the analog of a green function in the Deligne-Lustig character formula. Green function of Deligne-Lustig from their 1974 paper. Right now, it's just a philosophical statement that it sort of sits in the same position in the character formula, in my character formula, Jeff's and my character formula, in which it sits in their character formula. But in the depth zero situation, you can make this much more precise. And that's exactly what Stephen and Mark did. One of the things they did in their paper on depth zero L packets is that they proved that this is literally sort of an induction, inflation induction of a finite field green function. And then finally, notice that this inductive formula bottoms out. But I mean, it's all predicated upon reduction of a supercuspidal representation of a big group G to a supercuspidal representation of a smaller group G prime. So it bottoms out when there's no more reduction to be done, which is the depth zero case. And in that case, well, I don't have anything to say, but Debacker Reader in 2009 compute many such characters. Namely, the ones that come from Deligne-Lustig representations on the finite group of Lie type side. Questions so far? Okay. So to me, this story is endlessly fascinating in its own right. But Stephen pulled me aside after the last talk and said, you might want to spend a couple minutes talking about who cares. So I'll phrase it slightly more diplomatically as why. Why would we do all this? Now, if you ask Paul Sally, if you ask my advisor, he'll tell you a very simple answer. Harishchandra Harishchandra's philosophy of harmonic analysis, exegeticized, if that's a word, by Sally, is characters tell all. Once you know the characters, you know everything. And he really made this the cornerstone of his analysis, of his theory of harmonic analysis on real groups. Everything started with the characters. Now, it's a sort of funny thing that as you've seen from this workshop so far, as you'll see in the conference, there's an enormous amount of work that's been done in p-adic harmonic analysis, and very, very little of it involves characters in any essential way. So you might say, ha, you're wrong, it's useless. But my retort to that, why haven't we used characters much in p-adic harmonic analysis, is because until recently we haven't had any. As you may notice from the dates, the only really general character formulae we've got have been in 2009. So we haven't had a lot of time to see the full extent of the use of general character formulae. But already there have been some successes. I find the following hilarious. Harishchandra proved in 1970 the existence of characters for general p-adic groups. Sally and Shalika computed the characters of SL2 in 1968. That's great. You compute objects before they're defined. Of course, you can do it by hand in the SL2 case, but that's still something. So Sally Shalika in 1969 computed the Plancherel formula for SL2. I'm not going to write it down over and over, but every reference I'm giving you here uses character formulae in some essential way. So they computed the characters in 68. They used them in 69 to prove the Plancherel formula, to write down, I should say, explicitly the Plancherel formula. Much later, in 1984, they used it to compute Fourier transforms of orbital integrals. On SL2. I didn't appreciate this difference until recently, but I'm just going to make a big fuss about it. These orbital integrals we've got up here, or Fourier transforms of orbital integrals we've got in the character formula, are orbital integrals on the Lie algebra lifted up to the group via the exponential map, which are much, much simpler objects than semi-simple orbital integrals on the group. So this is a much bigger accomplishment. According to Harishchandra, I think some paper in 69 or something, when you're trying to do harmonic analysis, the Fourier transforms of group orbital integrals is what you're trying to do. That's the central problem. NER in 86, and coming along behind, I myself in 2005, in my thesis, used character formulae to write down an explicit local Langlands correspondence for GLN with some conditions. NER had much fewer conditions. He needed to know that only that you were in the cyclic case. I needed many more conditions. I needed to be in the prime positive depth case. I should write a supercuspidal local Langlands correspondence. This local Langlands correspondence is now available in full generality for explicit full generality for GLN due to the work of Bushnell and NER. Yes, Bushnell and NER, but sadly they didn't get the memo and they didn't use characters for it, so they're not on this list. Stephen and Mark in 09 proved stability results for depth 0 supercuspidals. Again, using character formulas. Last year, Tasho Kaleta proved endoscopic transfer for depth 0 supercuspidals. And I think, I'm not quite sure if this is done yet or if he's just working on it, but also for simple supercuspidals, the ones that Mark talked about yesterday. And Stephen and I are currently working on stability for positive depth supercuspidals. Specifically, the positive depth, the conjectural positive depth packets constructed by Reeder in 2008. Turns out the obvious, natural, canonical, God-given L packets he constructed, which are the only possible ones that you could ever consider, are actually not L packets. Their character sums are not stable. And there's essentially no way to see this except by writing down the character and noticing that the character involves this finite field Weil representation in a way that just messes with stability of L packets. Now, it's so canonical, it's so God-given that it can't be far wrong. And indeed, it isn't. You just need to toss a little quadratic twist in there. But still, you write down these packets. It is an utterly convincing definition. The only way to see that it needs adjustment is to write down the character formulae. So the general idea is that characters let us see the internal structure let us see the fine structure of L packets. In a way that just may not be visible from any other point of view. So what I want to wind up with, my last 10 minutes here. Yes?
In pushing on here, had you fix things with little twists?
Right.
Also, is it the same? I mean, did your observation coincide with theirs in the?
Yeah, it's. I forget the details, but so NER just describes it basically in terms of Kazhdan's automorphic induction, that on lifting paper. So he describes it maybe not completely explicitly, but in more generality. When I'm writing it down for these positive depth supercuspidals of prime degree or prime size GLN, that twist is much simpler to describe and is often absent. Oh. At the time I wrote it down, I wasn't thinking of things that way, and I can't remember well enough now to answer that question. Sorry. Probably, but I don't know. So I want to wind up with what next? Where do we go from here? There are a bunch of obvious questions. Anytime I've imposed a hypothesis, you could say, well, how about you drop that hypothesis? So for example, currently, the work with Tabaka relies on G prime being an unramified torus. No? Okay, so what if it's ramified? What if it's not a torus? The answer is, somewhat surprisingly to me, that the ramification is actually easier to deal with from the point of view of exactly what we're doing, which is trying to prove stability of certain character sums. Not worrying about Langlands parameters, just worrying, here's a sum of characters, is it stable? It turns out stability if two elements are stably conjugate, they're conjugate by something over the unramified closure. and that conjugation somehow doesn't see the ramification very much. So ramified turns out to be less of an issue than not a torus. We've got some partial results in this direction. What about endoscopic transfer? Everything is nice and explicit. In principle, we should be able to write down appropriate destabilized combinations and figure out to what they transfer. Famous last words, I suppose. This is just a lemma. How hard can it be to prove? But what I'm really interested in, and if you buy the philosophy that every advance in character formulae brings an advance in our understanding of harmonic analysis, what I want to do is remove the conditions, remove the compactness condition, in the Adler-Spice character formulae. And just as a reminder, that's the condition that G prime is compact modulo the center of G. Now, as far as proving things goes, that's kind of hard. But we have a clear roadmap ahead of us. And here's just a sketch of that roadmap. I'm going to start with oh, it's gone. That's poor board work. I'm going to start with a corollary of that theorem that was right here. You can probably see its ghost if you look very closely. A corollary of the theorem that Marty already mentioned, which is what happens to this character formula if you're very close to the identity. Well, close to the identity. Character value evaluated at gamma, all that gamma less than r stuff is going to drop out. We're going to try to take the Fourier transform of a semi-simple orbital integral on the centralizer of the head of gamma, which is trivial because we're close to the identity. So we're just going to get a Fourier transform with an appropriate normalization constant out front, a Fourier transform of a single semi-simple orbital integral. This is called single orbit Murnaghan-Kirillov theory. And it's been proven much more generally. This is the way historical accidents work. I love it. The fact that Murnaghan-Kirillov theory, the best citation for it is Kim and Murnaghan. So at least we got the right letters. Murnaghan. In 06, prove under much more general conditions. So P is still large, but for example, they don't even require supercuspidality. They certainly don't require any compactness condition. And they can write theta pi gamma is a sum over the nilpotent orbital integrals in G prime. G prime is the twisted Levy subgroup that occurred before. Of certain coefficients. So far this looks like the local character expansion, except notice my orbital integrals are coming from G prime. Times a combination of certain Fourier transforms of orbital integrals. They're no longer semi-simple, no longer nilpotent. They're somewhere in between. This is nilpotent orbits in G prime. Technically, they live on the dual Lie algebra, but it doesn't matter. When P is big enough, we can identify those with no trouble. If G prime is compact, even compact mod center, it has no nilpotent orbits, or rather it has one, and their formula collapses to ours. But I should know, this is not a new observation due to us. This has been known for some time. It's just an easy corollary of our character formula. And this happens for gamma near 1. Well, what about gamma far from 1? Notice what I've got here. I've got a character on G. So pi here is a representation of G, but it's expressed in terms of data on G prime. The next character formula I'm going to write down is also expressed in terms of data on G prime, but it's a character value also on G prime. This is due to Adler and Corman in 2007. Bless you. They didn't originally write it down this way because our gamma less than r, gamma greater than or equal to r stuff was not available. But it turns out you can rephrase what they said as saying that the character of pi prime, this representation on G prime, looks like a sum over nilpotent orbital integrals in H prime, and I'll write down what that is in just a moment. Of certain constants times Fourier transforms of certain orbital integrals. And this should hold for all gamma, near the identity, far from the identity, whatever. Near the identity, this term just drops out, and we're going to recover the Moynihan-Kirillov formula, where H prime is the connected centralizer of gamma less than r. In G prime, and just as a conjecture, I'm saved from having to write it down formally by the bell. A general supercuspidal character formula, again, still assuming that P is large, a general supercuspidal character formula should look like, should interpolate between Moynihan-Kirillov theory and the Adler-Corman local constancy results. In a certain well-defined way. All right, that's it for me. Thank you very much.